So yeah, like there's like a Canvas side with the exam score. It's just I mean you can actually look at the exam like a scan version. It's just the Canvas side is called the same as our regular side. It just has like exam from parentheses next to the name. So don't try to find it like on the regular Canvas side. Just go to that one. If someone is having issues like accessing it, just let me know. Overall, the exam scores were pretty good. But obviously, if someone has a question about their particular problem or how it was created, I think I enabled regrade request on the exam, so you can just do that. And I hope to post like the solutions to the exam like either tomorrow or Thursday latest. So you can also wait until then. Like the good thing about the exams being scanned is that there's really no rush for like making the request because like it's just like virtually there for eternity. So but yeah, like just let me write that down. So the exam score, like the exam access to the exam on the Canvas side that has the word exam.
What is it, 96?
Okay, so today I'm going to tell you about the second derivative class and the second and critical points. So as I mentioned, before the spring break, the next we only have one more class. So my idea is to be done with chapter 14 before the spring break starts. So between today and Wednesday. Let's just start with like a reminder of like top one critical points. So like in top one, if you have like a function of one variable, like y equals f of x. Right? When you have something like this, like for optimization problems and other types of problems, also curve sketching, you were interested in like finding the max and the mean of the function, right? Like, so typically they are called, relative maxima or relative minima, also a local max or local mean, because like, for example, let me show some of these in this graph. So this would be like a max, this would be a max. And the point of something like this is that, for example, this is only a maximum compared to nearby points, right? Like if you look further away from the graph, there are other places where the function can become higher, like for example here, or even here, like here, like the function is higher than here. So the point of a relative max or relative mean is that they're kind of like the max or the mean, like within like certain intervals, right? So this is where like in this picture, this is where the relative max are located. And in this same graph, this is where the relative mean would be located, right? So those are like how these two work. So relative mean, and relative max. So what you did in Cap 1 is that whether your max or mean, even in any of those two cases, you still have something in common, which is like the first derivative vanishes there, right? Assuming like, there was like a broader definition of a critical point, which was either the first derivative vanishes or like the first derivative is undefined. But in most applications, like to find the critical, like absolute value, for example, like the first derivative is undefined at absolute value at the origin. But like, for most applications, like when you when you would find critical points, you would say like the first derivative equal to 0. So let's just start there. Like, so step one would have consisted in like finding where the first derivative vanishes, right? Okay, and once you had the critical points, there was this second derivative test, maybe you remember it, that told you whether the the critical point would correspond to like a max or a min, right? So let's try to see what was the second derivative test. Then you would use second one to classify the critical points. So what did the second derivative test say? Let's say that this was one of the critical points, like at x naught. Here you have x naught. Okay, so what the second derivative test said is that like you would evaluate the second derivative at the critical point, right? And let's say it gave you like a negative value, right? That should correspond to like a max, if you remember that. How like there was like a fun trick to memorize this, which is like you draw a face of the same sign as the inequality, right? So since this is negative, you draw like a negative face, like someone like a sad face, and you see that there's like a max here. So that's like and then like I don't know if you like were taught that one, but it's like a convenient way to memorize um the second derivative test. And like likewise, if it's positive, like then you draw like a face, like which is you're happy, right? You're positive, like in positive mood. So like then you see like the mean. So let me so this one was like a relative max, right? Occurs when this occur when like it's negative, and the relative mean occurs when the second derivative is positive. So far so good. Now why, like, there's this question, and then it was inconclusive in the other case, which is when the second derivative vanishes, right? So the second derivative being zero, meant that it could be something like, could be like a max, or I mean, it could also be like an inflection point, like, it's just not enough to say from this alone what happens. So like, that's why you would say just like inconclusive, right? So it could be a max, a mean, or like an inflection point. Max, mean, or inflection point. Okay, now just I don't know if you did it this way, probably not, because like in Calc 1 you still had seen like the Taylor's formula, but there is like a reason why the second derivative test works, which is kind of easy to see. Why does this work? Does the test work? Because okay, so there's this Taylor expansion, right? So if you think about the Taylor formula, it's like, I mean, it said something like, well, the value of the function at a point, you can kind of expand the function, know the values of the function with respect to a different point, right? So what was like the formula? It is the value of the function at a reference point plus the first derivative evaluated at that point times x minus x naught, right? Plus 1/2 the second derivative evaluated at the reference point times x minus x naught squared, right? Okay, so this is like the only time in the course that I'll use calc 2. So nowhere else like I'll use it. Plus jump. Like, there's like either an error term, like there are different ways to write the rest of the expansion. You can put like an error term, or if it has like a power series, it just goes up to infinity. Like there's alternative ways to write it. But if you think about what this is saying, it's like, well, if you happen to choose x naught to be a critical point, right? If x naught is a critical point, then well, this is still whatever it is, but if you use as a reference point the critical point, then this first derivative goes away, right? Because a critical point is one where like the first derivative vanishes. So this is zero at a critical point. Is that making sense? So what that means is that in the expansion, in the expansion, only the quadratic, I mean, the leading term is really quadratic because the linear term goes away. So this is kind of like roughly like, this is like if you compare this with like, so if you compare this compared with y equals y naught plus, 1/2, like, you should compare this like to the equation of a parabola, like because it is quadratic, so it's really like a parabola, right? So so this is like a parabola. So what this is saying is that near like a critical point, right? Like near the critical point, the graph looks roughly like a parabola, which is what you see here. Like if you zoom in like a lot, it is more or less like some sort of parabola. It's not quite like a parabola because there's still error terms or like extra terms, but like at a first approximation, what you would see near the critical point is a parabola because the linear term goes away. So the concavity of the parabola is determined by this number a, but the number a is essentially the second derivative. You see what I mean? So like the second derivative determines the concavity of the parabola. Um, so the concavity is determined by. Is that making sense? And that's more or less where the second derivative test comes from. It's kind of like I mean, more or less like a consequence of like Taylor's formula. Now, so as you can imagine, there's exactly like like an analog of this story, like in our situation, right? So what would be what happens here, for our case? I don't know that before I say that, like, I don't know, so far so good. Any questions up to this point? Okay, so let me right, like our situation, like what's going on. And this one is a little bit harder to draw. But what happens in our case, we're going to use do this only for functions of two variables so that we can visualize the graph. So what happens in this case is that now you have a function of two variables and maybe the graph, again, you have to think of the graph as some sort of like terrain. Okay, this is harder to draw, but it looks a little bit weird, but what I'm trying to say, I'll show you some animations on GeoGebra in a bit because that's easier to see. But what I'm trying to say is like when it's like a graph, it's kind of like you threw a blanket in the air, right? So there will be max and mean. If you just like throw a blanket and let it like stabilize a little bit in the air. So like there's some relative max which are kind of here. There's a relative max here as well. So all these two are relative max, right? And for example, these two would be like relative mean, if that makes sense. Right? So the first thing is how would you locate them, right? Before, like, you would find the critical points, right? So the question is, what's the right analog of a critical point in this context? So the critical point before was where the first derivative is zero. Now, what is the version of the first derivative for us? Well, there's a couple of ways to think about it, but you can think of that being like the first partial derivatives that we can find. So here, like, if you have like the graph of a function of two variables, right? What is a critical point here is where like the two partial derivatives vanish, like the derivative with respect to x vanishes and the derivative with respect to y vanishes, or alternatively, if you like, it is where the gradient is zero, which is kind of a bit more geometric way to say it. So Um, so step one would be to find where the, the derivative with respect to x equals 0, and it's important that both have to happen like simultaneously. And the derivative with respect to y equals to 0. Okay, so you need both conditions to be true, or alternatively, as I was saying, this is the same as the gradient of the function uh, vanishing at a given point. So critical points are exactly the point where the gradient is exactly 0. That makes sense. And if you think about it in terms of the directional derivatives, because the gradient points where like the function goes is trying to increase, but if you're kind of reaching a max, the point is like the function kind of has stopped there, like in terms of growth. And the same kind of works the same with for the minima. If you just like flip your head, like turn it upside down. So it's kind of like the same argument. So that is what you get. And then the question would be is like, what, how can, like, once you find the critical point, which I'll do for you in a moment, how would you identify, whether that critical point corresponds to a max or a min, right? There's another thing that can occur, which are called saddle points. I'll tell you also about that in a moment. But the idea is that there is like an analog of the Taylor formula, which I'll just write for one time, which we'll never use again, but it's just to let you know that this is how where it comes from. So what would be the version of this test now? I'll keep this one here so that we can compare it. So the version of Taylor for our context is that like if you were to expand the function with respect in terms of a reference point, you have like the value of a function at an arbitrary point is the value of the function at a reference point. So these two terms look exactly the same, that it starts in this exactly the same way. Then the next term is partial, like derivatives, right? But now they become partial derivatives. That's what makes sense. So you would say something like the derivative of f with respect to x evaluated at the point x naught y naught times x minus x naught plus the first derivative of f with respect to y evaluated at the point x naught y naught times y minus y naught. So if you see like these, like I should put it in different colors. Let me just match them by colors. So this is essentially what corresponds to this, right? Like it just like you add another first derivative because now there are two first derivatives. So that matches perfectly. And then the fun thing that occurs is that then there comes like the second derivative contribution, right? And the second derivative contribution is that, well, there will be, there would be like 1/2 of the second derivative of f with respect to x squared times, well, this just means evaluated at the critical point times x minus x naught squared plus 1/2. Now there's another second partial derivative, right? Which is like the one with respect to y twice. So you put that here as well. And then there's y minus y naught squared. But what makes this a little bit more interesting is that now comes the mixed one, right? Like because there's also like the mixed term in partial derivatives. If you remember, like the mixed partial derivatives are the same, like doing x and then y is the same as doing y and then x. So that kind of gets counted twice. So that's like why you won't have like a 1/2 because it appears 2 times in the expansion. So you just get and blah 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 blah. It continues like that. So what ends up happening, like not just to not make this story too long, is that you know, at a critical point that this stuff goes away because, at a critical point, this stuff goes away because these are critical points. So the first derivative vanish at the critical point. And so like really like what happens near the critical point is determined by all this like stuff involving the second partial derivatives. So like what I'm trying to say is that it's still like the second partial derivatives that determine the, what happens with the behavior of the function. It's just that now it's like a little bit harder to identify because it's kind of like a competition of like, one, two, three terms, right? So it's kind of like three separate second partial derivatives like playing a role into what the graph of the function looks like. Okay. And that actually, if you wanted to analyze this properly, you would need like linear algebra to do the analysis, because what happens, just to like finish like this story, and then I'll show you what the results like the test says, is that you can kind of like arrange these partial derivatives into like a matrix, which is called the Hessian matrix, which we'll use in a moment. And again, if you ever take linear algebra, what happens is that this ends up being like a symmetric matrix, meaning that it equals C transpose. And that means that it has eigenvalues which are real and can be diagonalized, and that kind of determines what's happening here. But that's a long story that we cannot really go into detail. Because we like, linear algebra is not part of this course. But at least what I'm trying to say is like the behavior is determined by the partial derivatives of second degree. And it's just like a useful way to understand that, like in terms of like a matrix. And then you just have to analyze that matrix. But again, like I'll just tell you what the second derivative test says in this case. But before doing that, I'll just show you some pictures first, like just to get like a better sense of what's going on. And then yeah, we can move, we can apply this certain examples. Is that making sense? Are there any questions? Yes. What's the use of it? Okay, so for example, so right, like the thing is in I was saying that in the Calc 1 case, what the second derivative test says is that you kind of get like a parabola like this, right? What happens here is like you get some sort of paraboloid, you actually, or quadratic surface, actually, it's like a better, like, because it may not be a paraboloid. But you get something that looks like kind of similar. Right, you get something that looks kind of similar. It's quadratic, right? So it's like a quadratic surface, but it's actually, yeah, like a paraboloid. But the thing is that you get this mixed term, right? What you would call like a mixed term in general, because of this thing that depends on both x and y. And so usually what happens, you should think about this like similar, like to, for example, like, let me actually do it on algebra. I think it just will make everything easier. Just take advantage of it. So for example, and that's actually one of the things I was going to show you now, is that let's say you can have like something like this, like the parabola had been like x squared plus y squared, right? Then like we actually had seen this one before, right? Like it is like the usual salad bowl. Um, so it's kind of obvious that there's like a mean here, because it's like the sum of two positive quantities, right? So the mean occurs at the origin, right? Then you could turn it upside down, right? And by upside down, I just mean like, I just mean put like okay, this looks terrible. put like a minus in every, like in front of every coefficient, right? When you turn it upside down, you like, that makes sense. You also like, you turn like the max into a mean, right? But then like you could do something a little bit more interesting. Which is, imagine like, which goes back to my point of like the mixed term. Imagine that instead of having something that is something in X plus something in Y, you also have like a contribution that combines the X and the Y. So for example, you could have like plus X times Y, right? Okay, and now when you see the plus X times Y, okay, that's good because, I mean, you still see like there's like a mean here, but it's not super obvious maybe for you or like for most people why it would be, like it's not clear how would you identify that because of the mixed term. And what happens, let's see if I can make this, I think this will run. No, this is fine, but let's see. Oh, okay, this is cool. So if you change the coefficient of the xy, right? If you change the coefficient of the xy from being 1 to 4, you completely change the graph, right? There was like a value of, there was a special like threshold that I passed. And after I did that, like the graph has completely changed in behavior. This is actually what will be called like a saddle point, and I'll explain why in a moment. But what I'm trying to say is that then, like you see, like there's something funny happening where like, like these mixed terms, like depending on how, like, what they are, like they can completely affect like the pattern of the surface. And so what you would do like in linear algebra, if you ever take it, is that you kind of like assign a matrix to this, which is like the coefficients in front of the variables. So it would be in this case like 1, because there's a 1 here, a 1 here. And then like the mixed term is kind of like the off diagonal term. And because it's repeated, you kind of like put it like, and you half it, like, so you take half of it. And that ends up being like a symmetric matrix. And there's like a thing called like the diagonalization theorem that tells you that you can diagonalize the matrix, which means that you can kind of rotate the coordinate system so that this mixed term disappears after a rotation. So that is actually used like for the inertia tensor or matrix, if you like ever see that like in mechanics. But the point is that like you need like a way to deal with the mixed terms, and the proper way to do that is by linear algebra, which we don't do here. But that's essentially what like how the story goes. Yeah, so you do need to understand what happens there. But like actually, this is a good example of what is going to occur in general, where you will see like max or mean, and also this extra thing, right? So what, like, let's just focus on this extra thing for a bit. And in fact, you can get it just with something super easy like x times y. So if you do x times y, you already see something that qualitatively looks the same, right? As what I just showed you. So what happens there is that, if you look at the graph from this like direction, if you're approaching the origin, right? It's kind of like you're going down, right, to approach the origin. So like if you come from it from this direction, you would say, oh, this like looks like a mean, right? Because you're decreasing the value of the function to reach that point. But if you change your perspective, right, if you kind of like reach the graph, the origin from a different direction, like now to reach the origin, you kind of have to go up, right? So what this means is that actually this behaves as a max or a mean depending on the path that you take, and we want the max. If something is going to be called max, it has to be path independent, if that makes sense. So something like a max, like the one that like the max that that I was showing you before, like something like -1 minus x squared minus y squared, right? The reason why we want to call this a max is that it doesn't matter how you approach this point. Everyone has to grow in height. You have to increase your height regardless of where you are to reach this point, right? So that's why it's like a local max. And the reason why the other one, like the x squared plus y squared is what's called like a local mean, right? Is that like say to reach this point, there's no matter where you start on the graph, if you're going to get to this point, you have to decrease the value of the function, right? So the difference between those two and the other one, like which was x times y, is that in the case of x times y, okay, this is x to the y, which is a little bit more complicated. That's not what I wanted. X times y. The difference with x times y is that whether you're a max or a min kind of depends on your perspective of how you approach the critical point. Okay, and these are the ones that will be called saddle points. They're just like whatever is not a max or a min. And so, but yeah, so my point is that that's kind of like the difference like of the three categories that appear. And the second derivative test will tell you which, like how to identify these, if that makes sense. Is that okay? Are there any questions? So far, so good. Okay, let me write for you what the second derivative test says, and then we can apply in some examples. Yeah, just in case like you came late, I was just mentioning that if you want to look at your exam, just go to the Canvas site that has the word exams on it, not the regular one. So. I'm going to give you the second derivative test for a function of two variables. So here, like the first step is to find the critical points. So first step is to find critical points. And by that, you have to solve. So for this, you must solve the equations. Like you get like two equations that you need to find the equations. Okay, so after you found, let's call one of these, let's say P is a critical point called P. One of these critical points. Okay, after you have the critical points, you build what's known as a Hessian matrix. So maybe I should step two is like you find the critical points. P is one of those. Then step one. Step two is to construct the Hessian matrix, and that's kind of like the key player in the second derivative test. So you build the Hessian matrix. H, so H is for Hessian. So it's just like the matrix of second partial derivatives. Okay. Okay. And then once you have a 2 by 2 matrix, one of the quantities that you can find is its determinant. Okay. The determinant is really like an important number associated to any matrix, which is squared. So in this particular case, you can compute its determinant, okay? And then find determinant of H uh, of P. And so what does this mean? It means the determinant evaluated at this particular point. So this means the determinant of the matrix evaluated at the critical point. And again, I'll do all of this in a moment with a particular example. Sorry, of the matrix, yeah, of the matrix evaluated at the critical point. And the second derivative test essentially depends on what this number is. So the determinant, if you remember, like it's just a number. And what we care about in this case is like its sign. So whether it's positive, negative, or zero. That's like the first thing you have to look at. So that you study the sign of the determinant quantity. Okay, so again, let me just say it in the easiest way possible. So if the determinant is zero, like the determinant could happen to be zero. So case determinant of H is zero. If the number gives you zero, the test is inconclusive. So it's the least interesting example, like situation for us, but like it's kind of like the analog of before, like of having second derivative being equal to zero. Like so here the test is inconclusive. So in practice, like you will rarely encounter this because I did apply the second derivative test to classify critical points, but it's something that can occur like in the real world, let's say. Okay, so that's the first possibility. The second possibility is when the determinant is negative, that's also when it's a negative number, P will yield a what's called like a saddle point. So in this case, P, the critical point P corresponds to a saddle point. And that just mean what is a saddle point? It is a thing that I show you in the animation. It's like a max or a min depending on the way you approach the point. So it's like or a better way to say is that it is a critical point that is neither a max nor a min. So this is a critical point. Which is neither a max nor a min. Nor a min. So it's kind of like path dependent, if you want to think about it that way. Whether you're a max or a min depends on the path that you took to get to that point. So it's kind of like a path dependency. So it's a path dependent max or min. It looks like a max or a min depending on which path you take. And that's not good if you want to be a max or a min. Okay. So and the last case, like it's just too bad that this board is so small because I'll try not, like, I guess I'll have to raise it once we do the example. And the last case is just the case where like the determinant is a positive number, right? So And then kind of in this case, like what happened is not entirely determined by this determinant. You also have to look at the second partial derivative. For example, like with respect to x. So let me write it here. Just give me a second. For the example. So if you look at the second partial derivative with respect to x, evaluated at that critical point, if this is positive, so if this happens to be a positive number, what does that mean? The same phase works that I showed you earlier. So you do like a positive phase, so P corresponds to a local mean, okay? And if the second partial derivative with respect to x has to be ends up being a negative number, then you can still do the phase and P yields a local max. That makes sense. I'm about to show you how this looks like, but maybe just questions about that first, like how I'm stating this. Yeah.
Of the question matrix of points is once you look back at the second year.
Right, so it's kind of like you still need extra data, and the data can, I mean, there are other ways to do it, but the data, the extra data that you need would be this first entry of the matrix. What,
So we already solved.
right, like you don't have to recompute it because like it was, you had to find it anyways to, you know, to find the determinant, but like it just like, it's like, oh, pay more attention to what this first entry of the matrix was, and from there you can determine it, yeah.
Is it possible for the second derivative in terms of x to be 0?
Oh, right, like that's a great question, because what happens if this is 0, right? If you put a 0 here, right? The determinant, it would be this number times this number, which we want to contribute, minus this number squared, right? So let me, actually, I think I still have enough room to write it here, like the formula for what the determinant is more explicitly. Right, so the determinant is like the product along the first diagonal, which is this quantity minus the second product. But this product, since these two are the same, is being squared, right? Is that making sense?
Yeah.
And then if this can happen to one of these happens to be 0, right? This first contribution goes away, and that makes the determinant definitely can never be like, you know, like since you have minus the square of a number, at best this would be 0, right? But it's always non-negative, like sorry, non-positive. Like, so it under the assumption that the determinant is positive, right? If the determinant is positive, that does force like the second partial derivative with respect to x to be non-zero. That sounds reasonable. No, but yeah, that's a good question, because it is kind of implicitly hidden in this condition, that having positive determinant, actually having positive determinant forces the two entries along the diagonal to be non-zero. And actually you could have done, like you could have stated this in terms like of the second derivative with respect to y. It's just that it's more convenient to state it with respect to x, because then it looks more closely closer to what you do in Calc 1, if that makes sense. Yeah,
Oh, yeah, so that means that we can use the second derivative with respect to y.
you could have like done exactly the same thing here, but instead of putting x squared, well, x, you put y. So like the analysis would still work in exactly the same way. It just looks a little bit asymmetric because again, we're not kind of using the language of linear algebra. If you wanted to use the language of linear algebra, it's like actually there's like a matrix has something that's called the eigenvalues. And then you would ask whether like the eigenvalues have the same sign or opposite signs. And that would be kind of like the replacement for, yeah, I'm sorry, if the eigenvalues are both positive or both negative. And that's like a more like elegant way of like writing something like this. So it's, but yeah, like it also, you can also do it for like the second with respect to y, that in practice, like, it just looks better to put it with respect to x because it looks more familiar, like, again, more similar to like the statement in Calc 1. But yeah, like really, it does require like linear algebra for this to be stated like in the best possible way, if that makes sense. Okay, so let me do an example just to kind of land on something a bit more concrete. Okay, so let's say the function had been so we'll graph it in a bit to like show you how it looks like, but for now, like you just have this function and you want to identify like, the critical points and determine whether they're max, min, saddle points, what are they, okay? So all these problems have like a part that's entirely computational in terms of like the derivatives, which is just find the partial derivatives. So my recommendation for this problem sometimes is just to find all the partial derivatives that you need. So which ones do you need? You need like the derivative with respect to x and the derivative with respect to y, but you also need these second derivatives to assemble them into the matrix. So you might as well just compute everything from the beginning of the problem so that you don't have to go back and like find them again. So the derivative with respect to x would be what? This gives you x squared, this doesn't contribute, then this gives you 2y, right? And minus 6. So that's the derivative with respect to x. Let's put it in a box. The second derivative the derivative with respect to y. Would give you 2y plus 2x minus 3. Okay. And then, okay, so those are this is all that you need for the critical points, but just to do compute all the derivatives that are needed anyways, let me, find those out. So the second derivative with respect to x is just take an extra derivative here, right? So you just get 2x. Then you do the mixed one, so which is xy. So xy just means like take the derivative with respect to y of this one.
I have a computation.
Oh,
about the first
I may
one.
have done something wrong here.
So why is it, plus 2y? I feel like it should be plus 2y plus another 2y minus 3y.
Okay,
to get you to the-
You're referring to this?
Yeah.
Okay, let's see. So this again, with respect to x. Okay, so this one gives you x squared, right? It's with respect to x, so this one gives you nothing, right?
Yeah.
then this is
Oh,
two,
wait, I forgot. It was opposite.
right, yeah. Is that okay?
Yeah, no.
Okay.
Yeah.
No, because like, yeah, it's like, there are a few derivatives, so it's always better to double check every step before, you keep going. And then, okay, so this is xy, and then, yy is a last one needed. And so just take the derivative with respect to y one more time here. And you get a two as well. So this is like accidental, the fact that these two coincide, right? Like in general, there's no rule that says that they have to be the same, just like a coincidence. Like it depends on the specific function. So it's really better to think of them as three separate computations, right? And so the matrix that I'm calling H is XX in the first entry, XX is 2X, right? YY in the fourth entry, right, the last one, which is just happens to be 2. And the off diagonal terms are like XY. So again, just happens to be 2 and 2 here, right? And like in general, all of these entries could depend on X and Y. It's not that this is like, it's not that it has to depend only on X. Like there's nothing like of that sort as a rule. It really is like a function, like every entry is allowed to depend on X and Y because every entry here, which is like a second partial derivative, can be a function of X and Y. It's just that like for all these problems, to make them tractable, they kind of have to have like easy second partial derivatives. Otherwise, like it just takes like an eternity. So it's more like an accident of the time, that we want to spend on like solving any of these problems. But I think MyLab does have like a few problems which are a bit more like crazy in terms of, like the partial derivative. So like you can check those, which you'll see more general things like appearing as the solutions. But it's kind of just to show you that everything that involves partial derivative is kind of already computed here. You needed like the first partial derivative, and also you needed the second partial derivatives, which I'm like arranging into this matrix form. Is that okay? Is that making sense? Yeah.
How did you, find the combined second derivative?
So you like that means like do x and then y, or y and then x. That doesn't matter. So if you do x, you already have it here, and then you just have to take the derivative with respect to y. Is that okay? Good. Okay, so we have everything in place. So let's start finding the critical points. Like the only thing that I really need is this part. So hopefully the rest will fit in the middle. So. Okay, so step one is to find the critical points. So for that, you need the derivative with respect to x to be 0, and the derivative with respect to y to be 0, and that gives you a system of equations. So in every single one of these problems, you get a system of equations, one equation for each partial derivative. So you have to solve something like this in this particular case. Is that okay? Is that making sense? So we need to solve this system of equations. Like again, like the equations that you have to solve in practice are not too crazy. Like so, usually a simple method of substitution or like subtracting the equations, adding them, like doing something of that sort would be more than enough to solve these equations. Like, for example, one thing you could do if you like, you can say like again, there are many ways to do this. You can say that if you call this equation 1 and this equation 2, since you notice that there's like 2y in both of them, if you subtract them, then that basically gets rid of the 2y. Another option would have been to solve for 2y here and then just plug it into the other one. So it's kind of like up to you, but if you do it this way, you just get x squared minus 6, and then I'm subtracting the equation 2. So the 2y's go away, and then this becomes minus 2x, and the other term becomes plus 3, right? Because you have to change the sign. You have to change the sign in every term of equation 2. And then this is not too bad. you get x squared minus 2x minus 3 equals 0. And again, like usually you just need to remember here how to factorize. So you get what x minus, let's see, is it x minus 3 times x plus y equals 0? I think so, right? So you get that. So you have two possible values for x, right? So what are the possibilities? So x equals 3 is a possibility, or x equals -1, right? What happens if x equals 3? You can find the corresponding value for y, for example, by saying that, from this equation, you also could have said that 2y equals 3 minus 2x, or that y equals 3 minus 2x over 2, right? So like you see, like the y value is determined by x. So if x equals 3, what's the corresponding y value? That is 3 minus 2x, so it's 3 minus 6 over 2. So it's like -3/2. And if x equals 1, what's the if x equals -1, what's the corresponding value for y? It's 3 plus 2 over 2 is like 5/2. So what does that mean? In this particular case, it means that we have found two critical points, right? So like the critical points are this value with x together with this value for y, or this value of x together with this value of y. So let's see. Let me put it here. Is that okay? Are there any questions about this? So far, so good. Is that making sense? Okay, and once you have the critical points, the next step. Okay, actually, you can forget about the first derivative. You can forget about all of this. We already used it because we already assembled the matrix, and we already used the partial derivatives to analyze to find the matrix. So let me erase all of these except the Hessian matrix, which is like the only thing that we need at this moment. So step 2 is to find the Hessian matrix, right? So step 2, what is the determinant of the Hessian matrix? What's the determinant of this matrix? Well, it's like the product along the first diagonal is 4x, right? Minus the product along the second, like the off diagonal terms, which is 4. So it's 4 times x minus 1. Okay, so that's the determinant. And what the method says is to evaluate the determinant at the critical points, right? So for example, let's start with P1. What's the determinant of H of the matrix evaluated at P1? That just means 4x minus 1 evaluated at P1, but P1 means that x equals 3 and y equals -3/2, right? The y is completely useless in this case because like the particular shape of the formula for the determinant, but in general it could have been useful. So if you put it at 3 here, you get 2 times 4, you get 8, right? Is that making sense? So this number at this particular critical point happens to be positive, right? And so you go through the cases. We're not here, we're here, right? So then you have to look at the second partial derivative with respect to x. So you ask, I think, okay, this is going to be positive. So let's just put it right? So it happens to be positive. So since it's positive, it gives you what, a local mean. So one of the critical points will be a local mean, and that's what we just found.
Does it have to be the derivative with respect to, singular with respect to X, could you do it with respect to Y? or
You
X
could
and
have
Y?
done it y, but in this case, it would have to be one of the two along the diagonal. So it could have been either with this one or this one, and you see that both are consistent, right? Because the point is that what happens is that if the determinant is positive, right? If you look at the formula for the determinant, I hate when this happens. I don't know why this is turning so on. But if you look at the formula for the determinant, for this to be positive, x and y, those two partial derivatives need to have the same sign. They don't need to be the same value, but they do need to have the same sign, if that makes sense. Yeah.
Could you also look at this and say that because secondary y doesn't depend on a variable?
Well, not, right, like, yes, like in this case, right, like you could have seen it from the two here, that it had to be like a mean. But if, like, what I'm trying, I guess what I'm trying to say is like, if this number had happened to be -1, that would have forced this to also be negative as well. So like they go in pairs, like they have the same sign when you are in the positive determinant case. If that makes sense. But like, for practice, like all these derivatives will be relatively easy to evaluate. So, like in terms of like amount of time, like there's not much of a difference, but yeah, like conceptually, that is what's happening here, because if that makes sense. Anyone else? Okay, so we already know that one of the critical points is a mean, and what happens with the second critical point? This one is actually a bit easier. What happens with the determinant at the second critical point? Well, that's 4x-1, right? Like the formula for the determinant is the same, but now we evaluated at different values, right? So now it's x is -1 and y is 5/2. Again, the y value plays no role here, but in other functions it would, like, so it really is function dependent. And so when you put -1 here, you get -8, right? The important thing here is not so much that there was an 8 here, it's just like it is negative, right? So you are in the case where the determinant is negative. And negative determinant, what does that yield? Saddle point, right? So P2, so P1 is a local mean, and P2 is a saddle point. Is that making sense? I think it's the first. Okay, so just like to finish, like in the remaining minutes, let me show you like the graph. Of this. I know every second derivative test problem is essentially of this sort. Like, you find like a function of two variables, or you're given a function of two variables. You find the critical points, and then you classify them using the second derivative test. So I didn't know, I think I may have mentioned this earlier, but like one of the things that happens on the second exam is that it's very like narrow what you have to do for any type of problem. So if it's a second derivative problem, you always have to do the same thing. It's not like kind of these problems about lines and planes where there's like a lot of variation depending on what information you're given. Here, like it's always a function, and from that function, you have to do always the same stuff. So like the problems like in this part of the course, like they tend to be more like direct in terms of like what you have to do to like solve them. They can be a bit like algebraically tricky, like depending on what like the system of equations is, but it's always like exactly the same procedure. So let me just finish off today. By telling you. By showing you how this function looks like. So. It is. The function was. One-third x cubed. Plus y squared. Plus 2xy. Minus 6x minus 3y. Okay. Oops, sorry, let me, like the graph. Like I need to zoom out for the graph to look less weird, so. Okay, now, it looks a little bit better. Let's see. Okay, so. I don't know, like, if you can see, like, okay, yeah, sorry about this graph, but. It's kind of like clear, hopefully, that there is a mean here, right? And that is essentially, that is the mean that we found before, right? And then the saddle point is like a bit harder to see in the graph, but if like the saddle point is kind of like there, so like if you look at it from this angle, you do see like your like from this perspective, it looks like a max, but if I start rotating the graph, you'll see it will look like a mean. So that's what makes it like a saddle point. So let me see if I can rotate this without it making it look crazy. Oh yeah, cool. It's just like there's a lot of purple in the like superimposed, but like it looks better on the. Let me see if I can change the color. So that like the saddle point that I was referring to was this, and like if you kind of follow, if you follow this part of the graph again, it kind of looks weird just on the projector. But if you follow that part of the graph, it looks like kind of you have to fall down, like decrease your height to get there. So like the point of a saddle point is that it's a max or a mean depending on how you reach it. And that's not okay if you want to be called like a max or a mean. So max or mean are kind of like regardless of the trajectory you use to get there, like either you are always increasing the function or you're always decreasing it. Saddle points is like depends on the path that you take, whether it looks like a max or a mean. Is that making sense? Okay, so next time we'll do a different type of problem, which is called the Lagrange multiplier problem. I'll tell you what is that about on